All right, so I've pre-agenda items for today. One is to talk about homework 3, and also one last bit of stuff to cover about time-dependent problems, and then if there's any time left over, that'll be for ongoing homework questions. So, those of you who are wanting to do homework 3 will be delighted to know I was able to resolve my issues in getting that problem, problem 6, to work, and then sure I'll carry over to problem 7. Now, the funny part is my code was actually correct all along. It's just that how I was checking whether it was correct was flawed. Actually, there's one thing I need to check, and I meant to check on this before class, and I completely forgot. Okay. About V cycles and stuff. Okay. Nice. Okay. So I'm going to give an outline based on my code of how to solve, how to pursue problem 6. Then I'll give some pointers about problem 7, because problem 6 is 1D and problem 7 is 2D. Okay, I might as well have my code up in front of me to help with that. Okay. So here are the files that you ought to have. One is a testing script. So that's what you would actually run. That's going to call any functions that you have. And its job is to set up the original right-hand side, B. That's given in the problem. It's just that weird function from homework 1. And then where that function evaluated at the interior points, and then call your multigrid function, which I'll talk about last. The second item is function for smoothing, and that would be by some sort of iterative method, Gauss-Seidel or SOR. And the interface for that would be very simple. Some function x is equal to, you can call it whatever you want. Maybe it will be Gauss-Seidel if you want to call it that. And all it needs is a matrix and the right-hand side. So its job is to solve iterative methods. But you don't want to solve, it seems good. You don't want to solve it completely. You don't want to iterate to full convergence because, first of all, why would you need multigrid? Second, it'll just take too long. I've written this with for solving this system in a problem of Gauss-Seidel or SOR with various choices of a relaxation parameter. It's pretty dang slow. So that's something. So you wouldn't want to do it that way anyway. You want to iterate maybe a certain fixed number of iterations, or maybe iterate to a certain generous tolerance, like not something really small, like maybe 10 to the minus 3 or whatever. And I'll talk more about that at another point. So you think of it as partially solving Ax equals b, because its job is not to solve Ax equals b, is to make the error in x smooth to set up multigrid, and that's where the last function comes in. And the output of it would be x, and your input really would just need to be B. Whatever your right hand, actually I'm going to call it not B, but R. So that is your residual, but that is initially B. So the first time you call it, like from your test script, B is what you would pass in. Now, the length of B should be some power of 2 minus 1. So the idea is, if you have power 2 minus 1 interior points, that means that h is equal to 2 to the minus m. Because we're solving on the interval 0 to 1. And the problem wants you to solve this for m equal to 15, which means you have 32,768 grid points. So it's a lot, but MATLAB can handle that. Might take some time, but it will. Okay, not sure how much was missed there, but this is your outline. I don't think very much was missed, but okay. So I'll give more details about restriction in a moment. So you get a new residual called RC, C for course. Once you have that, then call multi-grid again with that course grid residual. And it will go ahead and solve. And what's output is your error estimate. And I call it CEC, error on the course grid. Then you interpolate your course error to fine grid of spacing h. That gives you your error that's on the fine grid, and then you update your solution. That's it. So what will happen is multi-grid will keep going down to a coarser grid until the grid is so coarse, less than 100 points, it just solves the system, gives you that error, and then the whole thing bubbles back up. So basically, this recursion naturally does a V-cycle. Okay. Now, I need to describe the restriction and interpolation. So restriction, both of them are going to be implemented by matrix vector multiplication. So restriction, you have a vector on your fine grid, and you want the output to be a vector on a coarser grid. So many points to fewer points. So restriction is going to be a rectangular matrix like this. Not so many rows, many more columns. And what you do is averaging. So if you have a scaling factor of 1/4 out front, then you do 1, 2, 1, 1, 2, 1, 2, 1. Wait, that's wrong. Okay. So what ends up happening naturally is the number of columns is n, which is 2 to the m minus 1 columns. And then the number of rows is going to be n minus 1 over 2, which turns out to be 2 to the m minus 2 over 2, which is 2 to the m minus 1 minus 1. So it's the next power of 2 down with half as many subintervals. So what you need to do is construct that matrix, but you want to use you want to use sparse matrices. This is definitely a sparse matrix. Most of the entries are going to be 0. So what this has the effect of doing is averaging trios of points together, giving a point in the middle the most weight to get the new value. So in other words, to draw what's happening here, here are your 3 find points. Here's your 1 coarse point. So these are given weights of 1/4, 1/2, and 1/4 to get the value at this 1 point. So because all the weights should sum to 1 and be positive. So that is restriction to a coarse grid. On the other hand, interpolation, after doing this, is easy because all you have to do is, I'll call it I, which I know is inviting confusion because I is identity. But, well, I'll give a proper notation here. H to 2H. So from fine grid to coarse grid, and this is coarse grid to fine grid. It turns out to be just 2R transpose. So if I write out what that is, so this takes a shorter vector on a coarse grid, gives you back a longer vector on a fine grid. I'm going to make sure I'm getting this. Yeah, okay. So that will have entries, okay, 1/2, 1, 1/2, 1/2, 1, 1/2, 1/2, and so forth. So what this has the effect of doing is, by matrix vector multiplication, the first point in the fine grid will be half the first value in the coarse grid. So you have this coarse grid value goes by half to this point, and then it just gets copied, the 1 here, to the next point, and then to get this point, these 2 coarse values are averaged together with weights 1/2 each to get this point. Now, the reason why we weight this value only 1/2 is this interpolation operator assumes that the value here is 0. So it's linearly interpolating between here and 0. So that's why there's this weight of 1/2. At first I thought that was wrong, but I realized, oh, yeah, okay. So these are matrices that get you between grids. So you have to create those matrices as efficiently as possible. Now, first, any questions? Now, I should mention that's the 1D problem. 2D problem, you know how to set up a matrix in terms of a 1D problem. It's Kronecker product with identity in both ways. 2D, so restriction operator in 2D is the restriction operator in 1D, Kronecker product with itself. And then that would mean that the interpolation operator in 2D would be 4 times the restriction operator in 2D transpose. It's 4 because you have 1/2 twice. Okay, so at least you have a simple relationship in 2D also. So once you've done the 1D problem, the 2D problem won't be so bad. Okay. Now, I have to tell you about my difficulties with multi-grid yesterday. Because here's what I was doing. After I implemented all of this, I would check the error at every step by examining the residual. So what I would do, for instance, I would look at the residual before I updated with the error, and then again after. And I found that there was no improvement. And as I went back, up from my courses grid up back into my finance grid, the residual norm kept getting worse and worse. It's like, what the hell's going on and it was just completely baffling me. What I would do is I would plot my fine grid vector and my restricted vector, or the other way, my coarse grid vector and my interpolated fine grid vector, and look at the plots. Beautiful match, so no issue there. It's like, well, what is this? And I finally solved the mystery by plotting a great many vectors, and here's what I found. I would get an error vector on the coarse grid. I plotted it. That looked something like this. So kind of like a sine function vanishing at the boundaries. I think this is what I tried simpler right-hand side function to get this. Okay, so this is my error. And then I would E and EC. So coarse grid, fine grid, they both look the same. Then I multiplied both of them by the appropriate A, for coarse grid or fine grid. And here's what I found. For the coarse grid, everything was fine. What I would expect is that this would be differentiated twice, therefore amplified by the frequency, but you get something in the same shape. So this is A coarse grid times E coarse grid. So no problem there. Then what I would do is also multiply in a fine grid. Now, these guys matched. When I multiplied by A, they did not. It behaved like this. Heavy oscillation. It was awful. So this is, okay. I thought, what the hell's going on here? So then I started looking at the individual entries of these vectors, just the first 10. And here's what I found. Every other entry is 0 of this highly oscillatory vector. Like,
oh, because keep going, sorry.
Well, you think why?
Not how you say it.
Okay. All right, but if you turn out to have guessed right, then you can hit yourself.
Okay.
Okay. Well, how on earth is that be happening? And then I realized what's happening to get from coarse grid to fine grid interpolation. But what kind of interpolation? Linear interpolation. So what happens is, if I have these coarse grid values, and I want to get to fine grid values, these at the same, when the points match up, they're just copied. But what happens otherwise is an averaging of neighboring points. So I should make these values different. So to fill in, so coarse grid is all I have. Fine grid at this point in the middle. The way this is done is linear interpolation.
And so,
and when I am multiplying this by a matrix that performs second differentiation,
oh,
tell me.
the second derivative of a linear
function is 0.
Exactly.
Yeah, and I thought, well, then do I have a lousy interpolation operator? Should we do something different? But this is what they all recommend. Like, you look at all the sources they do this. Like, okay, well, then maybe this is not what I should be measuring. So I thought, okay, let's forget about residual. I'll just go ahead and use backslash to compute an exact solution to compare against and look at error rather than residual. And the error was beautiful. It was nice and small. And it stayed small. I was like, oh, so my code was working all along. I just had no idea because I was looking at the wrong thing to judge its effectiveness. So, very nice lesson for all of us. Also, and the thing is, I would say in every numerical linear algebra class, we can look at error, we can look at residual, but the thing is, just because one is small does not mean the other is small. And I always say that in a theoretical, abstract sense, like, oh, your error could be small, and your residual could be large, you just never know. And now it's finally happened. Like, this actually happens out in the wild. So, yeah. Okay, so Baptism of fire by the non-multigrid person. Yeah, so that was a relief. I didn't have to try to like make up something else for you guys to do. So those of you who want to do multigrid, I believe there are at least 3 of you, probably 4 of you. It's safe to do so. All right. So now I will see how much of this I can do prior to the break. Because the other thing I found was, yeah, when I did this check of, okay, here's the solution before I add the error correction, and then after. Yeah, it's tremendous difference. Because the error was actually pretty lousy before correcting, and then like made a difference of like several orders of magnitude. It's like, wow, this multigrid stuff really works. No wonder people talk about it so much. Okay. So I'm still talking about systems of ODEs that arise from PDEs. I'm done talking about specific methods. Yesterday is all about that, run the cutout, multi-step, etc. But now it's more about how we analyze the effectiveness of these methods. So, so we have a system of ODEs. This is a linear one. Y prime is equal to a y. And initial condition, y is 0, is some given vector, y naught. The solution, we have a formula for the exact solution. It's e to the at y naught. And all of these methods, run and cut, multi-step, for a linear problem, they have the effect of approximating that exponential by some polynomial or rational function. And the solution, yt, is said to be stable if all of the eigenvalues of A have a real part that is negative. So in other words, you get exponential decay in your solution rather than exponential growth. So this would lead to the absolute value of the exponential of these eigenvalues to be less than 1. And the typical problems we look at, like for instance diffusive problems, we're supposed to have exponential decay anyway. So the thing is, if we have like explicit Euler versus implicit Euler, we have, it has a very simple form for this kind of linear problem. So you're just multiplying each solution each time by this matrix for explicit Euler. And this is the first 2 terms in the Taylor series of e to the a delta t. Whereas for implicit Euler, you have identity minus delta t a inverse yn. So it's really like you took the first 2 terms in the Taylor series for e to the minus a delta t, and then took the inverse of that. So it has the approximate. So that also. So I might call these both some matrix M. M's job is to approximate e to the a delta t. Just does it in different ways. So what we want for stability is that all the eigenvalues of M, whatever M is, need to be less than 1 in absolute value, which could be complex modulus. So we have very different pictures for stability for explicit Euler versus implicit. So with 1 plus identity plus delta t a, in order for the eigenvalues of this to be less than 1 in absolute value, we must have 1 plus delta t eigenvalue has to be less than 1, but that means that even if the eigenvalues of A have a negative real part, to match the underlying system of ODEs, we are so delta t lambda is restricted to a disk in the complex plane that is centered at -1 and has a radius of 1. So delta t or lambda must be small enough so that all of these, for all the eigenvalues of A, fit in this disk. So if the eigenvalues of A, any of them, are particularly large in absolute value, delta t must be really, really small. So that's something that's quite unfortunate. So it is conditionally stable. On the other hand, for implicit Euler, we must have 1 over 1 minus delta t. We must have that satisfied. So in other words, we need the magnitude of 1 minus delta t and IA greater than 1. But the thing is, if we're assuming the problem itself, the solution itself is stable, so these eigenvalues all have negative real parts. So if a real part of this is always greater than 1. Therefore, the magnitude of this complex number is definitely going to be greater than 1. So this is unconditionally stable. So there's two things at play here. Is the system of ODEs itself stable? That's if the eigenvalues of negative real part. Once that is settled, assuming the problem itself is okay, is your method okay? And that's in case if the eigenvalues of m are less than 1 in magnitude. So we're going to assume throughout that the system of ODEs itself has stability. We just need stability of the underlying method used to solve it. And we see that implicit Euler always gives you that. But explicit does not unless you have a tiny time step. This is why stiffness is bad. Because you, as your spatial resolution increases, your eigenvalues of A become larger in magnitude, so delta t must be even smaller to compensate and keep things stable. Although implicit methods, your matrices get more ill-conditioned, which also creates problems, just of a different sort. Okay. All right. Now, what's important about this is this allows us to take fewer, larger time steps than with an explicit method. This is why implicit methods are worthwhile, because for an implicit method, the time steps themselves are more expensive than for explicit methods. But if you can take fewer of them, then that would balance out, or maybe you could even get ahead. So that's what makes implicit methods viable, because you can take fewer time steps. In fact, for instance, heat equations, generally implicit methods are used for that reason, because the time step restriction for explicit methods like explicit Euler is so severe that it makes explicit methods prohibitive, except KSS. But yeah. that's immune to this analysis here. Making method is different enough, and it's like, forget about that. Okay. All right. Okay. So actually, a couple examples. All right. Okay, just to illustrate issues of stiffness and stability. So first example, this deals with a system where A is 2 by 2. Even a 2 by 2 system can be problematic numerically. So A is just minus 50, minus 50, 49, 49. And my initial data is vector 2, 0. So in this case, the exact solution can be written down. Just take my word for it, because I'm not going to take a matrix exponential here. As two terms, e to the minus t, 1, 1, plus e to the minus 99t, minus 1, 1. Now, the second term quickly gets small because of that 99 in the exponent. So if you were to plot the solution, pretty much all you would see is this term. That's much larger. But the presence of this term in solution causes a terrible time step restriction for methods like explicit Euler. So it's those negligibly small terms. It's those negligibly small terms that have large derivatives. That's the problem. These terms have enormous derivatives compared to these. So even though this doesn't contribute to the solution, the derivatives overwhelm the derivatives of these. So that's what leads to these severe time step restrictions, even for a relatively small system. So what you end up needing a much smaller time step than what you really need to actually represent a solution like a plot. More pertinent example, heat equation in 1D using our usual centered difference. So we have our typical matrix that will probably stick a scene by now. And the spectral radius of A, so these eigenvalues can actually be computed. So it's bounded by 4 over h squared. And the eigenvalues are real. So for explicit Euler, requires that 1 minus 4 delta t over delta x squared. And I have a minus in here because all the eigenvalues of this are negative. Okay, must be less than 1. So if you were to expand out this inequality to try to get a condition on delta t, I won't do the algebra here, but you end up with delta t must be less than or equal to delta x squared over 2. So the problem with that is, as you increase the number of grid points, because it's that delta x squared, that means your delta t must be even smaller. This is a terrible time step restriction. Like for wave equations, it's a linear relationship. You shrink delta x by a factor of 2, you shrink the time step by a factor of 2. That's bad enough, but this is far worse. And this really illustrates why people tend to use implicit methods for these kind of diffusion problems. As an alternative, though, the Crank-Nicholson method, which is called semi-implicit, it's kind of like an average in a way of, actually in one sense it literally is an average of implicit and explicit Euler. So you apply half of that explicit Euler term on the right side, but then the other is evaluated at time n plus 1 and moved to the left side. So now you do a matrix vector product, and then you solve this system. So it's like doing the work of explicit and implicit Euler both. So the eigenvalues of M are equal to 1 plus delta t over 2 eigenvalue of A over 1 minus delta t over 2 eigenvalue of A. But the thing is, the eigenvalues of A have a negative real part. That makes the denominators, the denominator larger in magnitude. These are always less than 1. So Craig-Nicholson is unconditionally stable, just like implicit Euler. Now you might think, well, if both methods are unconditionally stable, why would you use Craig-Nicholson? Because Craig-Nicholson requires a little more work per time step than implicit Euler because of the extra matrix vector product. But this is second order accurate, whereas implicit Euler is only first order accurate. So you can have a best of both worlds thing going here with Craig-Nicholson's very popular method, which is why I included all my papers to show that KSS or my other methods kick its ass. It's one of the methods that people always suggest. Why don't you compare against this? Like, yeah, I'll kick its ass again. Okay, so I'm trash talking numerical methods, but anyway, can't help it. So the key is having this negative real part that makes the real part of this larger in magnitude than the real part of this, because the imaginary parts of this, these numerator and denominator, are equal in magnitude. Okay, where are we at? Okay. I have one item left, but I'll break now, cover that, and then we'll see what we have time for. Okay.
Okay, so earlier today when you said that with the multigrid you were looking at error by using like the backslash at first the like exact solution, are you talking about essentially just
Cheating.
I mean, well, yeah, but no, I mean, like doing finite difference and looking at with grid spacing 2 to the minus 15.
Yeah, so I don't mean exact solution of a PDE.
Yeah.
I mean exact. Okay.
Yeah, I see what you mean there. So, but when you're using that kind of grid spacing, I get an error that the array exceeds maximum array size preference.
Are you sure you're dealing with a sparse matrix?
This was when I did like when I was just making the matrix like with zeros. That command, like saying zeros in my 2 or in my.
Wait. Which matrix were you making with zeros?
I was filling up like before you get matrix D. Like I was looking at the finite difference code that we used for homework 2.
Right. But which matrix were you making using zeros?
I guess you were calling it A.
But what does it have in it? Like, what? Tell me about the matrix. What are you putting in it? Are you using the zeros command to make a matrix of
yes
2 and 15th?
Yeah.
No.
Okay.
I thought all along, back to homework 1, we should have been making matrices using like SP diags.
Yeah, I was. Hold on. Let me find it again.
Yeah, because I mean, a full matrix of that size, MATLAB won't tolerate. It has to be sparse from the beginning.
Okay, I guess like. Yeah. Okay. I'll come to that.
Okay, so how are we doing it before?
I was making like you told us to like make F and stuff beforehand, like
Well, yeah, that's fine, but
yeah,
if
I think
that
that I
goes
was just like, okay, so I'm gonna make D beforehand. Like that was.
So we're using SP diex before in upper problems?
Yeah, I was using it after that though. I don't know. Or wait, I don't know what I was doing. Never mind.
You're confusing hell out of me.
I don't know. I'll comment it out.
Okay.
If you don't know what I'm talking about, it obviously is an essential part of it.
Okay. All right. So.
Oh yeah, it was something that I'd used, and then yeah, okay. I was an idiot. I forgot what I had done to the code to change it. Anyways, sorry. Never mind. Stupid question.
Okay. All right. Okay. So, all right. Very last tidbit to cover. Non-Neumann stability analysis. Okay. Now, this is non-Neumann stability analysis is a very convenient way to determine if a finite difference method is stable, particularly for linear constant coefficient problems. And the idea behind it is very easy to describe. So given a finite difference scheme for a linear constant coefficient PDE, what you do is you assume your initial data, so basically like UJN, which is an approximation of the exact solution at point xj time Tn. You just set it equal to e to the I k xj. And the reason for that is UJN plus 1 will end up being equal to some factor g of k times e to the I k xj. So this is called the growth factor. That's letter G. So that gives you an idea as to how much your solution is amplified, if at all, by time stepping using this scheme. So for stability, we need the magnitude of this growth factor to be less than or equal to 1 for all values of k, for all frequencies k. So it's just because when you plug this in to your method, working with exponentials, just the algebra works out so nicely that you can easily figure out what this growth factor is. All right, so to give an example, heat equation with a constant coefficient D. I guess if you try it with variable coefficient, what will happen is that your growth factor won't depend on just k. It would also depend on x as well. So you might still be able to get like an upper bound for a growth factor for all x. It just complicates things. So let's think of constant coefficient here. Now, if the initial data is e to the I kx for some k, that means the exact solution, if we assume like periodic boundary conditions, and that's what we'll do here, because e to the I kx is 2 pi periodic. What you get as your exact solution is e to the minus d k squared t times e to the I kx. So this is your growth factor for the exact solution to u k. And because we have a negative exponent, then that condition is satisfied. So the exact solution doesn't experience growth over time. So now we want to try solving this numerically and see if we can get the same thing to happen. So if we use explicit Euler in time, and we use central differencing in space. Also, that's a method you're familiar with. Yeah, okay. So that would be Ujn plus 1 minus Ujn over delta t is coefficient Uj plus 1n minus 2Ujn plus Uj minus 1n. This is why I use superscripts for time, because it lets us use subscripts for space. Delta x squared. So what I can do is substitute e to the ik xj. So Ujn is e to the ik xj. And Uj plus 1n is going to be, that'd be e to the ik xj plus 1. Now, if we assume equal spacing, which we're doing throughout, that's going to be the same as e to the ik delta x e to the ik xj, because the difference between xj plus 1 and xj is just going to be delta x. So that way we can see that, well, similarly, Uj minus 1n is going to be e to the minus ik delta x ik xj. So you can see that every single entity in this scheme is going to be a multiple of e to the ik xj. The only thing I haven't accounted for is Uj n plus 1. Well, that has my unknown growth factor, so I'm going to call that capital G, e to the ik xj. Now, G is going to depend on k, but I'll just write it as G. So the idea is, now I'm going to substitute all of this stuff into here, everything, and solve for G. And then I will determine whether that can be made less than or equal to 1 in absolute value, like under what conditions. Now, the algebra for this is all done in the notes, so I won't repeat it here. But what you get, so you solve for G, and what you end up with is 1 plus r e to the ik delta x minus 2 plus e to the minus I k delta x. And you can see where this comes from the center difference in space. The factor r is a shorthand for capital D delta t over delta x squared. All right. So we want to try to simplify this to get an idea of how big it can get. Now, these two terms, the exponentials together, e to the I theta plus e to the minus I theta, that's the same as 2 cosine of whatever theta is. So that's 2 cosine k delta x. So I can simplify G to be 1 plus 2r cosine k delta x minus 1. Now, cosine is always less than or equal to 1. So therefore, this whole thing is less than or equal to 0 because r is positive. Therefore, this whole factor is guaranteed to be less than or equal to 1. But I need absolute value of G. to be less than or equal to 1. So this is not enough. So I need this to be greater than or equal to minus 1 as well. So if I work with that now, okay, so 2r cosine k delta x minus 1 must be greater than or equal to minus 2. I'll cancel the 2's. I'm going to negate both sides, which will flip the inequality. Okay, so really what I need is over r. Okay. Let's see. Oh, actually. Now, this is equal to, if I Taylor expand cosine, first term of it is going to be 1. So then I'm going to get k delta x. Okay. Yeah, k squared. Oh, sorry. That's not really what I'll look at. Because this has to be true for all k. And the thing is, when is this going to be at its, this whole expression is going to be at its largest. So the worst case is when k delta x happens to be equal to pi, because then cosine of pi is minus 1. So this whole expression is less than or equal to 2. So that means that 1 over r must be greater or equal to 2, therefore r must be less than or equal to 1/2. So if I fill in what r is, I need d delta t over delta x squared must be less than or equal to 1/2. Okay. So once the grid spacing delta x is chosen, delta t must then be chosen small enough to make that true. And because of the relationship between delta t and delta x squared, that is a very severe time step restriction. So this is why explicit methods are not so good for explicit finite difference schemes, like explicit Euler, are not so good for these kind of problems because that delta t has to be so small. Okay. So questions about that? So whatever it is has to be true for all k. So we find out what makes this as large as possible, and that's where we got that is less than or equal to 2. Now, on the other hand, for the same equation, if I use Crank-Nicholson, dang it. Okay. What happens there is I have uj plus 1 minus, uj n plus 1 minus uj n over delta t is equal to d times, instead of the second derivative at time n, I have 1/2 the derivative at time n plus 1 plus the second derivative at time n. So like I said, it's an averaging of forward and backward Euler. So what I do is when I make the substitutions, I make the same substitutions in here, but I did over there. So this would become, that's an n. So this becomes e to the I k xj. This becomes e to the I delta x. K delta x. E to the I k xj. And so on. Here you'd have the same substitutions, except you have to include the growth factor g. So in fact, here's an easier way to make this substitution. Just for shortcuts in the algebra. Because if you substitute everything times e to the I k xj, every factor is e to the I k xj. It all cancels out. So we just let ujn is equal to 1. Uj plus 1n is equal to e to the I theta. Uj minus 1n is e to the minus I theta, where theta is equal to k delta x, shorthand for that. And then for time n plus 1, you multiply everything by the growth factor g. So when you make those substitutions in here, so for instance, that would be g e to the I theta. And this would be g e to the minus I theta. This would just be g there and there. So when you do all that, and the details in the notes, and you solve for g, what you get is 1 minus r, 1 minus cosine theta, over 1 plus r, 1 minus cosine theta. And what happens in this case is, because cosine theta is less than or equal to 1, here you're always subtracting something from 1, here you're always adding something positive to 1. Therefore, the denominator is always going to be larger than the numerator. So you get g less than or equal to 1 for any value of theta and r. It doesn't matter. And we see unconditionally stable. So you can try von Neumann analysis with other kinds of schemes to determine whether they're conditionally or unconditionally stable. So all it is you substitute the initial data, e to the I k x, and work out the growth factor. In 2D, similar idea, you let u of xj make sure I have my notation right. Okay. So u of x, y, t, n is replaced by e to the I kx plus ly. Because now, if you're in 2D, your frequencies are ordered pairs, k and l, instead of a single number k. So then you look for a growth factor that's a function of two variables, k and l. And so you want to make sure for all k and l that this growth factor is less than or equal to 1. And what I've done in the notes is carried out a von Neumann stability analysis on heat equation again on explicit Euler, and you get a similar condition as to that, except it's 1/4 instead of 1/2 because of it being 2D. Okay, so this is recognizing the fact that when you have periodic boundary conditions, what you get for your solution at the new time is always a multiple of the solution at the old time, and you'll see, does the solution grow from one time step to the next? So if you can guarantee that it won't, then you have stability. And if you also show that this method is consistent, like the local truncation error goes to 0, then what happens is you've proven a scheme is convergent because stability plus consistency equals convergence. And I will end this new material with was actually something meant to trip us up as grad students at Stanford on qualifying exams on this material. Because I mentioned how implicit schemes, like implicit Euler or Crank-Nicolson, tend to be unconditionally stable, whereas other methods like explicit Euler have a severe time step restriction. And so it would seem to be a contradiction that there actually is a scheme, an explicit scheme, called Dufort-Frankel scheme, that is explicit but unconditionally stable. And the reason why that's not contradictory is only for certain values of a certain parameter that it has is the method actually, or like for time steps small enough, is the scheme actually consistent. So that's a strange thing, that most of these schemes we see, consistency is easily established. It's always holds. But for Dufort-Frankel, it doesn't. So that's how it's able to get unconditional stability by not always being consistent with the PDE.
What was the name of it again?
Dufort-Frankel. So it was our favorite trick question to ask. Okay. I should mention that these restrictions on the time step are in keeping with what's called the CFL condition, Courant-Friedrich-Lewis condition, about how the domain of dependence of a numerical method must contain the domain of dependence of the PDE. This is especially true for wave equations in order to ensure, people think it's stability, but really it's ensuring convergence. Okay, now, in the last minutes that we have, I have no more notes, come to the end. Are there any other questions about, well, anything?
I have a question about that particular explicit Euler.
Yeah.
I mean, I've seen this formula many times, but I mean, I always had this question that why it is very similar to explicit. It is explicit Euler.
Yeah.
But in explicit Euler, we have over 2h, right? Why substitute with just delta t and ignore that too?
Wait, no, but the 2h, that's for a different kind of PDE. That's for like a wave equation, where you have a first derivative and center difference.
Okay.
Yeah. Okay. Yeah, if you have a one-way wave equation like ut equals ux, then you'd have like uj plus 1n minus uj minus 1n over 2 delta x. Other questions? It could be about homework, it could be about the oral final, it could be anything.
Oh yes, about the questions. 5, homework 2, 5, 2D part B. I know that you gave us the exact, but we have to solve it for C1, C2, and all those coefficients. And I don't know why I cannot get a unique, answer for those.
Okay, because actually, yeah, that's something I was working on with Abby last night, so maybe we didn't get the full story. Because what's really weird is, yes, you have these 6 constants, and you can get 6 conditions imposed on them by saying, like, well, it has to be periodic, and and continuous, and the first derivative also periodic and continuous. So that's 3 conditions for each. So that's 6. Yeah, that was not enough because you have a system into being singular can't be solved. So there's one more condition you can impose, and that is the mean of the exact solution has to be 0. In other words, the integral has to be 0. So if you work out the integral of your form of C1 through C6 and set it equal to 0, you will get a 7th equation. So now you have like a 7x6 system, which and MATLAB will be able to solve it.
And here's the okay. Oh, that's what MATLAB can solve it.
Yes.
I thought that would be And this integral is the summation of all these three because we separate
Right.
that to three.
Yeah, so you integrate each one of them over their respective subintervals, like 0 to 2 pi, pi over 2 to 3 pi over 2, 3 pi over 2 to 2 pi, add them all up. And I confirmed with a graph that it really did have zero mean. So that's one thing that was interesting about the rest of that problem. That setting up a matrix and solving doesn't necessarily ensure you get a zero mean solution. So you have to subtract out the mean and then compare it with the exact. Another thing that came up yesterday, this is for the, this is also for problem 5. For the Fourier differentiation matrix, if you do it that way instead of using the FFT, there's a typo in my notes that it was inherited from a typo in the MIT notes, and I consulted the original Trefethen text, which had it correct. That the so for second derivative, the diagonal entries. What it says in the notes is like minus pi squared over 3h minus 1/6. Is that what it was?
Yes.
Okay.
But
Wait, for the diagonal entries?
Yeah. This is for a Fourier matrix.
Yeah.
Page.
That's 5C, right?
I think so. Yeah. But I think it's on page 24 in the notes or something like that.
Yeah, I got it from that other notes that I showed you.
Okay. Yeah. Because I don't have those notes in front of me, but.
okay, so it is
I just want to confirm, but I have a correct formula that's in the notes.
pi squared over 3 multiplied by h. Yes, that new sign, and then minus 1/6. Yes.
Okay. So it's supposed to be h squared.
Right.
Down below. So both sets of notes had that wrong. I was looking like, why isn't it getting the correct solution? Then, oh, yeah. And actually, I noticed that even in Trefethen's text, showing the whole matrix and elsewhere in the matrix, there was a typo like missing a square, because all the off-diagonal entries are like cosecant squared or something, and he forgot a square. So every source was wrong in one way or another. Okay, so that's all the gotchas I'm aware of on the homework, and now we're, actually we still have 5 minutes left. So there's still time for any other questions.
Can I show you my board for 5A?
Right. Okay. Actually, velocity velocity is supposed to be f. Yeah, not just 0 minus f. But then, yeah, throwing the c in there doesn't change that. That's the key. So
I have to keep C here.
right. But the thing is, what I'm saying is, if minus Laplacian of u is equal to f, then minus Laplacian of u plus or minus c also equals f. That's because
Then inside of that thing, which is constant,
Yeah.
means that.
because it's Laplacian to 0 and won't change anything.
And is it enough, or I don't know how to show?
Because all the other stuff that's all that's fine. Okay. There are 3 minutes for any other questions anybody has about anything.
Last chance.
Okay, good. So I'm so done.